The sky above us seems still. The compass needle in your hand points north, unwavering. Yet beneath that quiet stability lies one of the planet's most restless forces, Earth's magnetic field. It hums invisibly through rock, water, and air, stretching far into space, shaping the boundary that protects our planet from the constant storm of the sun. But over the past century, that shield has begun to shift. Its strength is changing. The magnetic North Pole is moving faster than at any point in recorded history. And deep under the Atlantic Ocean, scientists have discovered a region where the field has grown weaker, a vast anomaly that may tell us something profound about how Earth works. The story of the magnetic field begins 3,000 kilometers below our feet. Beneath the solid crust and the slow-flowing mantle lies a sea of molten metal, the outer core. It's made mostly of iron and nickel, swirling and convecting under immense pressure. As this metallic ocean moves, it generates electric currents. Those currents produce magnetic fields, and together they merge into a single, global field that envelops the planet. Scientists call this natural dynamo the geodynamo. Without it, the Earth would be a very different place. The magnetic field deflects solar wind, streams of charged particles that flow from the sun. When that wind meets our field, it is guided around the planet, forming the magnetosphere, a vast teardrop-shaped region that shields us from radiation. This invisible bubble makes life on the surface possible. It preserves our atmosphere and keeps our instruments, power grids, and satellites functioning. Yet, even though it feels permanent, the magnetic field is always changing. Ancient lava flows show that the field has flipped completely many times throughout Earth's history, north becoming south and south becoming north. These geomagnetic reversals happen roughly every few 100,000 years, though not on a fixed schedule. The last one occurred about 780,000 years ago, and scientists suspect we may now be entering another period of significant instability. The first clues appeared in the early 20th century. When explorers and surveyors compared compass readings taken decades apart, they noticed a drift. Magnetic north was moving, slowly at first, then more rapidly. By the mid-1990s, it was racing from northern Canada towards Siberia at nearly 60 kilometers per year. For navigation systems that rely on magnetic reference points, this was more than a curiosity. It required constant recalibration. At the same time, satellites were gathering new kinds of data. Missions like Swarm, operated by the European Space Agency, began mapping the field in fine detail. What they found surprised researchers. Across the South Atlantic, stretching from South America to Southern Africa, the magnetic field was markedly weaker than elsewhere. This region became known as the South Atlantic Anomaly. Within it, satellites often experience increased radiation exposure, leading to data errors or electronic malfunctions. Some spacecraft even power down temporarily as they pass overhead to avoid damage. No one fully understands why this weak spot exists, but the leading explanation involves the movement of molten material inside the core. Deep beneath Africa lies a dense region known as the African Large Low Shear Velocity Province, essentially a massive upwelling of hotter-than-average rock. Scientists think that this structure may distort the flow of the outer core above it, creating patches where the field lines weaken or reverse. To visualize this, imagine a pot of thick liquid metal rotating slowly. If you stir it unevenly, small eddies form. Some swirl in the same direction as the main flow, others move against it. In the Earth's core, these counter-rotating regions can partially cancel each other's magnetic effects, producing localized weak zones like the South Atlantic Anomaly. Over time, those regions can grow or drift, influencing the field at the surface. Measurements from the past century show that the overall strength of the magnetic field has decreased by about 9%. That number sounds small, but in planetary terms it's significant. If the trend continues, it could indicate that a large-scale reorganization is underway within the core, perhaps even the early stages of a reversal. Still, scientists caution that weakening doesn't necessarily mean collapse. The field has fluctuated before and recovered. The key lies in understanding what drives those fluctuations. One challenge is that we can't directly observe the core. Every bit of information must come from indirect measurements, seismic waves, magnetic surveys, or simulations. Researchers use supercomputers to model how molten metal moves under different heat and pressure conditions. These models reproduce many of the patterns we observe, including the drift of the magnetic poles and the formation of anomalies. Yet they also reveal that the system is chaotic. Small changes deep underground can lead to large, unpredictable outcomes at the surface. Even with that uncertainty, scientists are confident that the magnetic field isn't failing. It's breathing. It waxes and wanes, like a heartbeat in slow motion. The weakening over the South Atlantic might simply be one phase of a long cycle that unfolds over tens of thousands of years. Still, the changes matter for modern life. Our satellites, for navigation, communication, weather and research, orbit within the magnetosphere. As the field fluctuates, so does the intensity of radiation they face. Engineers already designed spacecraft with shielding and fail-safes, but the anomaly increases the risk of single-event upsets, tiny radiation strikes that can flip bits in memory or knock sensors offline. On Earth, the impact is subtle but growing. Increased solar activity can trigger geomagnetic storms, inducing currents in long power lines or pipelines. If the field weakens further, those effects could intensify. This connection between the core and the surface, between molten metal and magnetic sky, reminds us how deeply our planet's systems are linked. The auroras that dance over polar skies are direct evidence of this invisible shield at work. When charged particles collide with oxygen and nitrogen high in the atmosphere, they release light, green, red, purple, the colours of our magnetic boundary shimmering in motion. When you see an aurora, you're watching Earth's defence system in action, a glowing trace of the same forces that move deep within the core. What fascinates researchers most isn't only that the field is changing, but that it changes in patterns that seem to have meaning, like the pulse of a living thing. The data suggests oscillations, reversals, and drifts that mirror cycles in heat, flow from the core to the mantle. Understanding those patterns could tell us not only about the future of the magnetic field, but about the energy balance of the entire planet. For now, we measure, we map, and we wait. Each new satellite adds resolution. Each passing year fills in another line on a magnetic diary that Earth has been writing for billions of years. If the shield is acting strange, it may simply be because the planet itself is alive with motion. And like any living thing, its heartbeat never stays perfectly steady. To study something you cannot see, you need patience and precision. Earth's magnetic field is invisible, silent, and vast. It passes through every object we know without resistance. Yet, for all its mystery, it leaves traces everywhere. In rocks, in satellites, in the movement of charged particles above the atmosphere. Scientists have learned to read those traces like a diary written in invisible ink. The first magnetic maps of the planet were drawn with compasses and guesswork. Early explorers noticed that true north and magnetic north did not align, and that the difference, the magnetic declination, varied by location. By recording this offset, they began to build the first global picture of the field. It was crude, but it revealed something important. The magnetic field was not fixed. It drifted slowly, bending and tilting over time. Today that mapping has become a global collaboration. Networks of ground stations record subtle magnetic variations from thousands of sites, but the most precise data comes from orbit. Satellites like Ørsted, Laschamp and Swarm have revolutionized our understanding of the magnetic field. Together, they monitor how the field changes across the entire planet, hour by hour, year by year. Each satellite carries sensitive magnetometers that can detect shifts smaller than a nanotesla, a billionth of the strength of a refrigerator magnet. They also track electric currents in the ionosphere and the magnetosphere, helping scientists separate local disturbances from deep planetary changes. The Swarm mission, launched by the European Space Agency in 2013, uses 3 satellites flying in formation. 2 orbit close together at about 460 kilometers altitude, while a third flies slightly higher. The difference in their data helps map the complex layering of magnetic sources, the crust, the mantle, the core, and space itself. What these satellites have revealed is that the magnetic field is a restless ocean. Waves of intensity roll through it. Small regions strengthen while others weaken. The South Atlantic Anomaly is the most dramatic, but similar features appear elsewhere. Some form and disappear within decades. Others persist for centuries. This constant motion hints at the turbulent patterns in the liquid core, an unseen dance of metal and magnetism that keeps the planet alive. To make sense of this movement, scientists use computer simulations called geodynamo models. These are virtual Earths built inside supercomputers, where equations of fluid dynamics and electromagnetism are allowed to play out over millions of simulated years. The models begin with heat rising from the inner core, driving convection currents in the molten outer core. As that fluid moves through Earth's rotation, the Coriolis effect twists it into spirals. Those spirals act like magnetic coils, reinforcing and sustaining the global field. Each model run produces slightly different outcomes. Sometimes the field remains stable for hundreds of thousands of years. Sometimes it flips polarity. Sometimes it collapses into chaos before reorganizing. In these digital worlds, reversals are not catastrophic. They unfold slowly, over thousands of years. The global strength drops, patches of opposite polarity appear, and eventually the field rebuilds itself in the opposite direction. When scientists compare these simulations with the magnetic record preserved in rocks and sediments, they find strong agreement. During past reversals, the magnetic field did weaken, sometimes to a fraction of its normal strength, but it never vanished completely. The planet continued to protect itself even in transition. Still, a magnetic field is not only a geological curiosity, it touches daily life in subtle ways. Every navigation system that uses a compass depends on it. So do drilling operations, pipeline engineers, and even wildlife. Many animals, birds, sea turtles, salmon and bees, can sense magnetic fields. They use them to migrate, orient and find their way home. When the field shifts, their inner compasses must adapt. How they do that remains a mystery of biology as much as physics. For humans, adaptation is technological. Every 5 years, the US and British geological surveys release an updated world magnetic model. It's a digital map used by smartphones, airplanes and ships to correct their navigation. When the magnetic North Pole began moving faster, the agencies had to release an emergency update ahead of schedule, a rare step that shows how dynamic the field has become. The next layer of research explores not the surface field, but the electric currents it induces in space and on Earth. When solar storms strike the magnetosphere, they compress and shake it, generating geomagnetically induced currents in long conductors like power lines. Engineers monitor these effects because strong storms can overload transformers or disrupt communications. The famous 1989 Quebec blackout was caused by such an event. It wasn't the sun alone, it was how the solar energy interacted with our magnetic shield. The weaker the shield, the more energy enters. That's why scientists care about regions like the South Atlantic Anomaly. When the field thins, radiation penetrates deeper. For satellites, that means electronics must endure higher particle flux. For astronauts, it means more exposure during orbits that pass through the weakened zone. The International Space Station encounters the anomaly on almost every circuit, prompting brief sensor resets and increased monitoring. Still, the Earth's surface remains safe. The atmosphere absorbs most of the remaining radiation, even where the field is weakest. What concerns scientists isn't danger to people, but what these changes reveal about the deeper planet. The core is where Earth's long-term evolution unfolds, and the magnetic field is our only window into that hidden world. To look deeper, researchers combine magnetic data with seismic studies. Seismic waves, vibrations from earthquakes, travel through Earth's interior, changing speed depending on the material they cross. By comparing how those waves bend and slow, geophysicists map density variations inside the planet. When they overlay that information with magnetic maps, patterns emerge. Hotter regions at the core mantle boundary seem to align with areas of magnetic instability. It suggests that the churning of the core and the convection of the mantle are linked parts of one grand system. That realization is profound. It means the behavior of our magnetic field isn't isolated. It reflects the planet's internal energy flow. The heat left over from formation and radioactive decay, moving outward through rock and metal, driving both plate tectonics and magnetism. Every shift in the field is a whisper from that hidden furnace. To catch those whispers more clearly, scientists are designing a new generation of instruments. Quantum magnetometers, using clouds of ultra-cold atoms, can measure the field with extreme sensitivity. CubeSats are being outfitted with miniature detectors to map local variations. Even deep ocean cables, which experience tiny electric currents induced by geomagnetic fluctuations, are being considered as long-term monitors. Each tool adds another layer to the global picture, a high-resolution film of Earth's heartbeat. When viewed over decades, that heartbeat pulses in surprising ways. The magnetic north pole doesn't follow a straight path. It zigzags unpredictably. The South Atlantic Anomaly grows and splits into lobes, as if stretching across the ocean. Field strength rises in one hemisphere while dropping in another. The overall pattern resembles weather, chaotic, dynamic, but not random. Like the atmosphere, it follows physical laws that we're still learning to read. Scientists sometimes call this study space weather for the solid Earth. It's an elegant phrase. It reminds us that the forces shaping our magnetic field belong to the same continuum that links the Sun, the solar wind, and the heliosphere. Our planet is not isolated. It's part of a magnetic conversation stretching billions of kilometers. In that sense, to understand why the field is acting strange, we must look outward as well as inward. The Sun, with its cycles of activity, its flares and coronal mass ejections, constantly tests the resilience of Earth's shield. When the solar wind intensifies, the magnetosphere flexes. Sometimes those interactions reveal weaknesses that might otherwise go unnoticed. Our field is both a product of the deep Earth and a participant in space weather, a bridge between inner and outer worlds. As we move further into the 21st century, monitoring this bridge becomes critical. The number of satellites continues to grow. Electric grids span continents. Navigation depends on stable magnetic models. Yet, all of these rely on a field that is in motion. Understanding its rhythm is no longer a scientific luxury, it's a necessity for a civilization that lives both on Earth and in orbit. The next questions scientists are asking are no longer about whether the magnetic field changes, but how far those changes might go. What does true reversal look like from the surface? How long does it last? And how would it reshape the delicate balance between Earth, the Sun, and life itself? If the magnetic field were a steady current, life would be simple. But the story written in stone tells otherwise. Across mountains, ocean floors, and ancient lava fields lies a magnetic record of constant change. It shows a planet that flips its magnetic poles again and again, a silent rhythm stretching back billions of years. When molten rock cools, the iron-rich minerals inside it align with the magnetic field, like tiny compasses frozen in place. Geologists can read their orientation to reconstruct the direction and strength of the field at that time. By comparing layers of different ages, they've discovered hundreds of geomagnetic reversals. These events are not rare, they're part of Earth's natural cycle. Yet, to us, a civilization built within a single magnetic epoch, they seem almost unimaginable. A full reversal takes time. It doesn't happen overnight. In geological terms, it is a slow dance between order and chaos. The global field weakens, sometimes to 1/10 of its normal strength. Small magnetic patches of opposite polarity appear near the equator and drift toward the poles. Over thousands of years, they grow, merge, and finally dominate. North and south switch places, and the field recovers. To a compass, the needle would slowly wander, lose direction, then settle, pointing the other way. The last major reversal, the Brunnes-Matuyama reversal, happened about 780,000 years ago. It left a clear signature in volcanic rocks from Hawaii, Iceland, and the Indian Ocean. Since then, the field has wobbled and weakened but never fully flipped. Some researchers think we may be heading toward another reversal, based on the decline in strength and the rapid drift of the poles. Others caution that such patterns have appeared before and reversed course. The magnetic field, they remind us, has moods. One of those moods is the excursion, a partial temporary reversal. During an excursion, the field shifts dramatically, but then returns to its original orientation. The best-known example is the Laschamp excursion, about 42,000 years ago. Evidence from Antarctic ice cores and Australian cave deposits shows that the field weakened to roughly 5% of its usual strength for several centuries. The magnetic North Pole moved southward, then wandered back. During that window, Earth's upper atmosphere was exposed to increased cosmic radiation, producing spikes in isotopes like beryllium-10 and carbon-14. Those isotopes are the fingerprints of solar and cosmic activity. When high-energy particles hit the atmosphere, they create these rare forms of elements. which then become trapped in ice and tree rings. By counting them, scientists can trace how much radiation reached Earth in the past. The Laschamp event shows that even a brief weakening of the magnetic field changes how the planet interacts with space. Yet, the world didn't end. Life persisted. Humans painted on cave walls. Mammoths roamed the tundra. The weakened field may have caused more auroras and slightly altered ozone chemistry, but it didn't trigger extinctions. The main lesson is resilience. The magnetic field may fluctuate, but the planet and its life adapt. That lesson tempers modern fears about reversal. It wouldn't be an apocalypse, but it would have consequences. During a reversal, the field's complexity increases. Many poles can exist simultaneously. The magnetosphere would become patchy, allowing more radiation to reach near-Earth orbit. Satellites would face higher risk, and some regions might see stronger geomagnetic storms. On the ground, power grids in high latitudes could experience more induced currents. Air travel near the poles might require rerouting during periods of intense solar activity. But none of these are beyond management. Technology can adapt, just as life always has. What fascinates scientists is not the danger, but the mechanism. Why does the field flip at all? The answer lies in the turbulent flow of the outer core. Computer models show that reversals occur when the usual pattern of convection becomes unstable. Picture a spinning sphere of molten metal. Normally, heat rising from the inner core creates orderly rolls aligned with Earth's rotation. But over time, uneven heat distribution or changes in composition can cause those rolls to buckle. When they do, parts of the field weaken or reverse. If the instability grows large enough, the entire global pattern reorients, a magnetic reset. Some simulations suggest that reversals may also be linked to what happens at the core mantle boundary, where heat escapes upward. Large stationary plumes of hot rock, like the ones beneath Africa and the Pacific, may act as anchors that influence how magnetic flux is distributed. When one of these regions changes shape or temperature, it could trigger a shift in the core's circulation, setting the stage for reversal. It's an elegant idea, slow geological motion at the bottom of the mantle, influencing the magnetic sky above. To test it, scientists look to natural archives beyond rock. Sediment cores from the ocean floor contain fine magnetic grains that align as they settle. These sediments accumulate steadily, recording magnetic variations over millions of years. By studying them, researchers can estimate reversal frequency. On average, the field flips every 200,000 to 300,000 years, but intervals vary widely. Sometimes millions of years pass between reversals, sometimes only tens of thousands. The pattern is irregular, more like weather than a clock. In addition to full reversals, these records show constant smaller fluctuations, secular variation, where the field's intensity and direction change on human timescales. This variation is what we're living through now. It's the same process that causes the South Atlantic Anomaly and the accelerating drift of the North Pole. Whether it develops into a reversal or stabilizes again depends on how the deep core behaves in the centuries ahead. For now, scientists are watching closely. Satellite missions continue to refine their maps. Ground observatories keep a steady record. The data feeds global models that can forecast magnetic drift for a few years ahead, useful for navigation, but still far from predicting long-term shifts. The system's complexity defies simple prediction. A reversal, if it comes, would likely begin unnoticed, its pace so gradual that generations would pass before completion. From a human perspective, the event would unfold like a slow wandering of the compass. Pilots and engineers would update reference tables, satellites would adjust orientation software. The auroras might move closer to the equator, painting skies that rarely see such light. In tropical regions, people might look up one night to see green curtains of airglow never witnessed before. This vision, unsettling yet beautiful, is what keeps the study of geomagnetism both urgent and poetic. It connects the deep interior of the Earth with the experience of the sky. When you stand outside at night, watching a compass needle tremble or an aurora shimmer, you're observing the surface expression of rivers of metal flowing thousands of kilometers below. Scientists sometimes describe the magnetic field as Earth's voice in space. When it changes pitch, the rest of the solar system hears it. Planets like Mercury and Mars once had strong magnetic fields too, but theirs faded as their cores cooled. Mars lost its magnetosphere billions of years ago. The result is visible: a thin atmosphere, stripped by solar wind, and a surface scarred by radiation. Earth's field is what spared us that fate. Its continued motion is a sign of vitality, not decline. Every fluctuation, every drift, is part of that living process. The strangeness we observe now, the weakening, the shifting poles, the expanding anomalies, might simply be the latest movement in a pattern that has repeated countless times before. For humans, it is new. For the planet, it is routine. The magnetic field doesn't warn or threaten. It whispers. It reminds us that even the ground beneath us is connected to cosmic forces, and that change, slow, vast, and invisible, is the natural state of every world. To understand why our magnetic field behaves the way it does, scientists often look outward. The planets of our solar system form a natural laboratory, each one shaped by the same cosmic laws, yet each with a different magnetic fate. By studying them, we can glimpse what might happen to Earth in the distant future, or what could have happened had our core cooled a little sooner. Take Mars. Billions of years ago, it had a magnetic field strong enough to carve its own magnetosphere. The evidence remains in its crust. Orbital measurements show bands of magnetized rock, frozen remnants of a vanished field. At some point, Mars's core stopped convecting, perhaps because it cooled too quickly, or because its smaller size allowed the inner core to solidify early. Without motion, the dynamo died. The shield collapsed. Solar wind stripped away the atmosphere over eons, leaving behind a dry world exposed to radiation. When planetary scientists speak of magnetic protection, Mars is their cautionary tale. Then there is Mercury. Despite being small and close to the Sun, it still has a weak but active magnetic field. Data from the Messenger spacecraft reveal that its core remains at least partly molten. That tiny planet bombarded by solar particles still maintains a faint magnetosphere, proof that even minimal motion in liquid metal can sustain magnetic life. Mercury's field is offset far to the north, giving its southern hemisphere stronger exposure to solar wind. The asymmetry shows that planetary fields can be lopsided, shaped by internal irregularities much like Earth's South Atlantic Anomaly. Venus, by contrast, has almost no global magnetic field. Its slow rotation and uniform mantle seem to prevent the complex convection needed for a geodynamo. Without a magnetic shield, its upper atmosphere interacts directly with the solar wind, creating a temporary induced magnetosphere. The result is violent stripping of ions, one reason Venus's atmosphere is so different from ours. The contrast between Venus, Earth, and Mars illustrates a delicate balance. Heat, composition, and rotation must align perfectly to keep a magnetic heart beating. Earth, for now, sits in that balance. Our outer core remains fluid, and our planet rotates fast enough to twist its convection into stable spirals. But when scientists model the distant future, they see a slow, cooling trend. The inner core will continue to grow as the liquid iron solidifies around it. Eventually, perhaps billions of years from now, the dynamo will fade and our shield will weaken for good. Long before that, the Sun itself will have changed, expanding and heating until no life can remain. The story of the magnetic field is also the story of planetary time, measured not in years but in eons. Still, that future is remote. For now, the field is vibrant, though restless. To watch it breathe, we rely on technology orbiting above us. The Swarm constellation continues to chart magnetic variations with high precision. Each satellite's data is combined to produce a global model, updated constantly. The readings reveal the field's layered structure, the crustal magnetism from ancient rocks, the fluctuating signals from the ionosphere, and the steady pulse of the core. In 2025, the European Space Agency introduced new processing techniques that allow Swarm's sensors to distinguish subtle signatures from lightning, ocean tides, and even rainfall. These short-term disturbances help scientists separate local noise from deep planetary change. The more precisely we understand those signals, the better we can predict long-term evolution. Every refinement brings us closer to a continuous magnetic weather map of Earth, a quiet counterpart to the meteorological maps we see every day. Meanwhile, the Juno spacecraft orbiting Jupiter provides another perspective. Jupiter's magnetic field is colossal, 20,000 times stronger than Earth's. Juno's instruments measure its structure and dynamics, revealing complex zones of reversed polarity near the equator. In essence, Jupiter's field is already what Earth's might look like during a reversal: tangled, multipolar, yet stable on the whole. Comparing the two gives scientists clues about how magnetic systems behave when they become unstable but not chaotic. Even the Sun offers lessons. Its magnetic field flips every 11 years, a rapid cycle driven by the motion of plasma beneath its surface. During those reversals, sunspots migrate and solar activity peaks. The process is turbulent but rhythmic, showing that magnetic reversals can be both frequent and survivable. Earth's reversals take far longer, but the physics is similar. Motion in a conductive fluid creates loops of magnetic energy that can merge, split, or invert. To interpret all this data, researchers rely on a new generation of supercomputers. These machines simulate the behavior of liquid iron under conditions we cannot reproduce in laboratories. The models use equations of magnetohydrodynamics, the same physics that describes the Sun's plasma. Each run takes weeks and generates terabytes of information, capturing how magnetic fields evolve, twist, and regenerate. The goal is not to predict exact events, but to understand tendencies, how a weak spot might grow, how a pole might wander, how a reversal might start. These models also connect to surface observations. For example, scientists recently traced the rapid drift of the magnetic North Pole to a competition between two strong magnetic patches in the core, one beneath Canada and one beneath Siberia. As the Siberian patch strengthened, it pulled the pole toward itself. Such discoveries make the field feel tangible, no longer an abstract force but a physical entity with moving parts. From orbit, satellites see more than strength and direction. They detect minor changes in electric currents flowing through the upper atmosphere. These currents, driven by interactions with the solar wind, link the magnetosphere to the ground. When the field weakens locally, the currents adjust, forming auroras or geomagnetic storms. In that sense, our sky is a screen displaying the core's unseen behavior. Even the oceans participate. Seawater is conductive, so as it moves through the magnetic field, it generates tiny secondary fields. Instruments can measure those to study ocean circulation, another example of how magnetic science reaches beyond geology into climate and oceanography. The magnetic field, once thought to be purely planetary, now helps monitor global systems at every scale. As we learn more, one theme repeats: stability is an illusion. The field is not a static shield but a dynamic interface between the planet and space. Its apparent strangeness today, the drifting poles, the anomalies, the weakening, may simply be the normal breathing pattern of a magnetic organism. In that view, reversals are not failures but renewals, ways for the system to reset and remain alive. Still, uncertainty remains. Could a reversal happen within a few thousand years? Could the South Atlantic Anomaly merge with other weak zones to form a new polarity? The data hints at possibilities, but no certainty. To prepare, scientists focus on resilience, designing satellites that tolerate radiation, updating navigation models regularly, and teaching the public that these changes are part of the planet's nature, not a sign of catastrophe. From a broader perspective, studying the magnetic field is also an act of humility. It reminds us how thin our margin of safety is, a sheath of magnetism separating life from vacuum. Every aurora, every compass reading, every charged particle deflected is part of that protection. When astronauts look down from orbit and see ribbons of light glowing over the poles, they are witnessing physics that begins thousands of kilometers below their feet. The next decade will bring even sharper eyes to this invisible frontier. The planned Magnet mission aims to combine data from multiple constellations into a single global map, updated in real time. Ground sensors in Antarctica and the equatorial Pacific will provide continuous calibration. By then, we may be able to visualize magnetic weather the way we now track atmospheric fronts, with live maps showing where the field is rising, falling, or twisting. Such a system would mark a new stage in planetary awareness. For the first time, humanity would watch the Earth's magnetic pulse as it happens. The shield that once seemed eternal would become another dynamic feature of our world. Observable, measurable, alive. And as we learn to read that pulse, we might begin to see patterns that echo far beyond our planet. Magnetic fields weave through galaxies, shape stars, and sculpt the universe itself. The same physics that bends a compass needle governs the vast structures of cosmic magnetism. Studying our field is, in a quiet way, studying the architecture of the cosmos. When people say the magnetic field is acting strange, they are right, but only because we are finally watching closely enough to see it move. Every creature on Earth lives inside the magnetic field, whether it knows it or not. It wraps around us like air, shaping countless processes that unfold quietly, beyond perception. We think of magnetism as something that belongs to compasses or magnets on refrigerators, but in truth, it is one of the most constant presences in our lives. Many species depend on it directly. Migratory birds are the most famous example. For decades, researchers puzzled over how they travel thousands of kilometers with such precision. Even on cloudy nights when stars are hidden, they stay on course. Experiments showed why. When birds are placed in controlled chambers where the magnetic field can be altered, they change direction accordingly. Inside their eyes, special molecules called cryptochromes react to magnetic fields through quantum processes. These reactions may allow the birds to see the field as patterns of light or colour overlaid on their normal vision. To them, magnetic north is not an abstract idea. It is part of the visual landscape. Sea turtles, salmon and eels show similar sensitivity. Hatchling turtles find their way across entire oceans, guided partly by magnetic cues imprinted at birth. When they return decades later to lay eggs, they navigate back to the same beaches, tracing invisible lines through water and time. In each case, magnetism provides a steady reference in a world of shifting currents and winds. Humans once shared a more direct relationship with the magnetic field. Before satellites and GPS, sailors depended on compasses to cross oceans. Explorers carried magnetic maps correcting for local deviations as they charted new lands. The needle was a silent guide pointing toward an unseen force that made orientation possible. Even today, aircraft, ships, and drilling systems use magnetic bearings as a backup reference. If satellites fail, magnetism still works. But modern life has added new layers of dependence. Communication, navigation, and observation all rely on technology that interacts with the magnetic field. Satellites use magnetic sensors to control their orientation in space. Power grids on the ground experience tiny currents induced by magnetic fluctuations. Submarine cables, oil pipelines, and rail networks all feel the field's slow rhythm. A strong solar storm coupled with a weakened magnetic shield can create electrical surges thousands of kilometers long. Engineers design systems to withstand them, but as infrastructure grows more interconnected, vulnerability increases. That is why space weather forecasting has become a discipline of its own. The same agencies that track hurricanes now monitor solar flares and coronal mass ejections. They issue alerts when large eruptions are expected to reach Earth, giving operators time to adjust. During such events, the magnetosphere flexes, currents surge, and auroras bloom across the sky. For scientists, it is a reminder that the magnetic field is both guardian and gateway. It protects us, yet also channels the energy that links Earth to the Sun. Even within the body, magnetism plays subtle roles. Human brains contain tiny crystals of magnetite, the same mineral found in magnet-sensitive animals. Whether these crystals influence our perception remains uncertain, but some experiments suggest we may unconsciously sense magnetic changes. In one study, participants sitting in a dark chamber showed measurable brain responses when the magnetic field around them was rotated, though they reported feeling nothing. If confirmed, it would mean our species still carries a faint echo of its magnetic awareness. Culturally, the field has always inspired awe. Ancient Chinese scholars built the first compasses not for navigation, but for divination, believing that magnetism revealed harmony between heaven and earth. In the Middle Ages, sailors called the magnetic north the star that never moves. Today we treat it as a physical parameter, measured and modelled, but its deeper symbolism endures. The idea of a hidden force guiding direction resonates across eras, yet that guiding force is not fixed. As magnetic north migrates, our maps must follow. The World Magnetic Model, used by smartphones and aircraft, is updated regularly to reflect the field's drift. The 2019 revision came earlier than expected because the pole was racing faster than predicted. It moved beyond the range of the previous model's accuracy. The change was not dramatic to daily life. Compasses still pointed, roughly north, but it was a reminder that even our sense of direction is tied to a moving target. For wildlife, Such shifts can have deeper effects. Migratory routes may slowly adjust. Regions of magnetic interference, like the South Atlantic Anomaly, could confuse animals that rely on magnetic landmarks. Marine biologists have documented temporary stranding events among whales and dolphins that coincide with magnetic disturbances, though causes are complex. The link between magnetism and behaviour remains one of biology's open frontiers. In agriculture too, magnetism leaves traces. Bees use it to orient their hives. Changes in the field might subtly influence pollination patterns. Some studies even suggest that seeds exposed to magnetic fields germinate differently, not through mystical energy, but through changes in chemical signalling triggered by magnetic sensitivity at the molecular level. For all its subtlety, magnetism also shapes what we see. Every aurora is a direct manifestation of its interaction with the sun. When solar particles spiral along magnetic lines into the atmosphere, they strike atoms of oxygen and nitrogen, creating shimmering curtains of light. The colours depend on altitude and gas type: green from oxygen at lower heights, red from oxygen higher up, purple from nitrogen. These lights are not random beauty. They are the visual expression of a magnetic shield in motion. When the field weakens, auroras appear farther from the poles. During strong solar storms, they can be seen deep into mid-latitudes: London, Paris, New York. People look up and feel wonder, unaware that they are witnessing a cosmic tug-of-war. The same event that paints the sky also tests our satellites and power grids. For scientists, these displays are both aesthetic and diagnostic. They reveal where magnetic energy is flowing and how the magnetosphere breathes. In the age of instant communication, auroras have become viral phenomena. Photographers chase them across Iceland and Canada, capturing their movement in long exposures. Online, millions watch from screens, connecting for a moment to a process that has been protecting life for billions of years. That shared awe is perhaps the most human response to magnetism, an instinctive recognition of something vast, invisible, and essential. Still, there is another layer to how humans experience the field, psychologically. Knowing that the planet's shield is shifting provokes unease. Headlines about weakening fields or possible reversals often sound alarming. Yet scientists emphasize perspective. The field has changed before, and life has endured every time. Awareness should inspire respect, not fear. The planet is not losing its protection. It is evolving through cycles we're only beginning to understand. Understanding brings calm. Knowing how the field works, why it moves, and how we adapt helps turn anxiety into curiosity. It shifts the narrative from danger to discovery, from panic about a fading shield to wonder about a living planet. The same magnetism that guides a bird home also guides our instruments in space. We are participants in its rhythm, not victims of its change. Each era finds its own relationship with the magnetic field. For early humans, it was mystery. For navigators, it was direction. For modern science, it is a key to the planet's inner workings. Perhaps the next stage will be awareness, the realization that our daily lives unfold within a complex magnetic system that links every creature, ocean, and gust of solar wind. When the night sky glows with aurora light, that awareness becomes visible. For a few hours, the invisible shield that holds our world together reveals itself. It flickers, fades, and returns, like a reminder that even in its strangeness, the Earth is steady beneath us. When you hold a compass, you are holding a story that began before life itself. The tiny needle's movement is the echo of an ancient process deep below your feet, the same process that shaped continents and guided evolution. It is easy to think of magnetism as something outside of us, yet it defines much of what makes Earth unique. The magnetic field is a record of motion. Every fluctuation in its strength, every wandering of the poles, reflects currents of molten metal moving at speeds of tens of kilometers per year. Those movements, in turn, mirror how heat escapes from the core, heat that has been flowing outward since the planet formed 4.5 billion years ago. To study the field is to study time made visible. When researchers model the field's past, they often describe it as a living archive. Lava flows, sediments, and even pottery contain snapshots of magnetic direction. Ancient civilizations baked their orientation into clay bricks, leaving behind faint signals that can be read today. By comparing them, scientists reconstruct how the field changed over millennia. The result is a magnetic timeline that runs parallel to human history, a reminder that our entire story has unfolded under a restless sky. That restlessness is part of the planet's stability. The magnetic field changes because the core is alive with motion, and that motion drives the conditions that keep Earth habitable. If the core stopped moving, the field would fade, the atmosphere would erode, and the surface would become sterile. The apparent instability of the field is actually a sign of health. It shows that the planet is still exchanging energy between its interior and the cosmos. From a human perspective, those timescales are difficult to grasp. The field's shifts occur so slowly that they pass unnoticed across generations. Yet, when viewed over geological time, they reveal a pattern of renewal. Each reversal, each anomaly is a reset, a moment when the deep Earth reorganizes itself. These resets may take tens of thousands of years, but they ensure the dynamo's longevity. The field is not dying, it is adapting. That idea carries a quiet philosophical weight. It reminds us that change is not always a symptom of decay. In nature, movement often means endurance. Rivers shift their courses but continue to flow. Galaxies rotate and evolve while maintaining their structure. The magnetic field follows the same rule. Its variations are the language of persistence. There is also humility in recognizing how little control we have over it. The same core currents that generate the field also influence tectonics, volcanism, and the slow drift of continents. These forces operate far beyond human reach. Our species, for all its technology, lives within conditions it did not create. We can measure, predict, and prepare, but we cannot steer the molten engine below us. Still, that does not make us powerless. Our awareness itself is a form of participation. By observing, modelling, and adapting, we become part of the feedback system that allows life to coexist with a changing planet. Knowledge transforms uncertainty into resilience. When scientists update the magnetic models used by aircraft and ships, they are translating the deep Earth's language into something humans can use, a partnership between ancient forces and modern understanding. The magnetic field also offers a lesson in continuity. Though it appears invisible, it connects everything on the planet. The same lines of force that pass through a satellite also pass through a migrating bird, a buried wire, and the iron in your blood. When the field pulses, the entire biosphere responds in subtle ways. It is one of the few phenomena that touches every level of existence at once. In that sense, the field is both physical and symbolic. It represents unseen order, the structure beneath chaos. It shows that stability does not mean stillness. The Earth's magnetism is proof that balance can arise from motion, that harmony can exist within constant change. At night, when the aurora glows, these abstract truths become visible. The green curtains of light above the poles are the field expressing itself, energy from the sun traced by invisible geometry. Watching them, one senses how small the boundary is between Earth and space, between protection and exposure. The same beauty that comforts the eye is also a sign of the planet's defense in action. Astronauts often describe auroras as living organisms. From orbit, they ripple like waves across the edge of the atmosphere, following magnetic contours that stretch thousands of kilometers. To them, the field is not a concept but a presence, a luminous shell surrounding the world. Many say the sight changes their sense of belonging. The field becomes a reminder that Earth is not an isolated sphere drifting through darkness, but a dynamic system woven into the fabric of the sun's influence. Back on the ground, few people think about that connection. We walk under magnetic lines every day, unaware of the silent currents above and below. Yet, in moments of stillness, holding a compass, watching an aurora, or seeing a satellite streak across the night, that awareness returns. The line between science and wonder blurs. We realize that the field, though invisible, defines the boundary between safety and emptiness. This realization has shaped art as well as science. Painters, poets, and composers have all drawn inspiration from magnetism's dual nature: order and motion, stability and change. The physicist Michael Faraday, who discovered electromagnetic induction in the 19th century, often spoke of magnetic lines of force as though they were living threads binding the universe together. Modern imaging now shows he was right. Those lines form loops and arcs that weave through the core, the atmosphere, and space beyond. What he imagined is now measurable. Each discovery deepens the metaphor. The field becomes not just a physical shield, but a symbol of continuity in a changing world. Its strangeness, the drift, the weakening, the anomalies, is the language of a planet adjusting to maintain balance. Seen that way, the current changes are not warnings, but reminders of resilience. Every generation finds its own mystery in the field. For ours, it is the question of stability in a time of rapid change. We build systems that depend on constancy, yet live on a planet that is never still. The magnetic field teaches the same lesson that climate geology and biology do. Survival belongs to those who adapt. Whether the field strengthens or fades, the key is to move with it, not against it. Perhaps that is why the topic draws fascination online. It feels both scientific and existential. When people read that the magnetic field is acting strange, they are responding not just to data, but to the deeper idea that even the planet's foundation shifts beneath time. There is something comforting in knowing that such movement has always been there, long before us, continuing long after. In the end, the magnetic field is not a problem to solve, but a relationship to understand. It ties the molten depths of the core to the breadth of the atmosphere, linking geology, weather, life, and thought. To study it is to study connection itself, and so the story continues, silent, steady, unhurried. The compass needle trembles, the aurora flickers. Deep below, liquid iron flows in endless circuits, writing the next chapter of Earth's magnetic history. If there is one certainty about Earth's magnetic field, it is that it will keep changing. The flow of molten iron beneath us will never stop as long as the core stays hot. That motion, unpredictable yet rhythmic, will continue to write the planet's magnetic story long after our era has passed. For scientists, the goal is no longer to stop or stabilize it. That would be impossible, but to learn how to live with its motion. Modern observation networks are beginning to make that possible. The swarm satellites remain the foundation of magnetic monitoring, but they are no longer alone. New missions, such as the NanoMagsat CubeSats and the upcoming Magnet constellation, are designed to fill the gaps between larger satellites. They record subtle, short-term changes that could signal shifts in the deep core. On the surface, observatories from Antarctica to Alaska provide real-time magnetic readings, feeding continuous data to global models. Every second, somewhere on the planet, the field is being measured. This constant watch creates what researchers call the magnetic pulse, a live feed of Earth's internal rhythm. In the past, updates arrived every few years. Now, they arrive every hour. The transition from static maps to dynamic monitoring is transforming the field from an abstract scientific concept into a living data set. Soon, visualizations will show how the field breathes, much like weather maps display pressure systems. Viewers may one day check the magnetic forecast alongside the weather forecast, a quiet acknowledgement that both systems shape life on Earth. The technology behind this progress is intricate but elegant. Quantum magnetometers, using atoms cooled close to absolute zero, can detect infinitesimal changes in magnetic strength. Arrays of such instruments will soon be placed in deep ocean cables, Arctic stations, and even aboard long-duration space missions. By combining all these measurements, scientists will build a three-dimensional model of the field that updates in real time, a digital twin of Earth's magnetism. Such models have practical uses. They improve navigation accuracy for aircraft, ships, and drilling operations. They help power companies prepare for geomagnetic storms. They allow space agencies to protect satellites by predicting when they will pass through high radiation zones like the South Atlantic Anomaly. But their deeper value lies in what they reveal about the hidden Earth. Subtle shifts in magnetic patterns can hint at movement in the core or changes at the boundary with the mantle. In that sense, the magnetic field becomes a diagnostic tool, a stethoscope pressed against the planet's heart. As measurement improves, so does curiosity. What might we learn if we could see the field in real time everywhere? Could we detect patterns that repeat over centuries? Could we link core behavior to volcanic or seismic cycles? These are the questions that define the coming decades of geophysics. The better we understand the field, the more we realize how intertwined it is with everything else, not just space weather, but the stability of climate and the deep energy balance of the Earth. Awareness of this connection also reshapes how we see ourselves. Humanity once thought of the ground as solid and unchanging. The discovery of plate tectonics in the 20th century revealed that even continents drift. Now, magnetic science completes the picture. Not only the surface moves, but the core beneath it shifts as, well, the entire planet is in motion, every layer influencing the next. To live on Earth is to live atop a symphony of slow, unseen flows. That knowledge carries a certain comfort. It tells us that change is normal, even on planetary scales. The field may weaken, poles may drift, anomalies may grow, but none of it means catastrophe. It means continuity, a dynamic balance that has persisted for billions of years. Each fluctuation is a reminder that the planet is alive, its inner forces still circulating, its shield still pulsing with energy. Still, that continuity requires observation. Without data, we would not know when the next reversal begins, or how the magnetosphere responds to an active sun. We would be blind to one of the planet's fundamental rhythms. That is why international cooperation has become essential. The magnetic field ignores borders, so must its study. Agencies from Europe, Asia, and the Americas share data freely, maintaining a global model that belongs to everyone. The field protects all life equally, and so its measurement is a shared responsibility. Outside laboratories, interest in the magnetic field is spreading among the public. Amateur scientists use smartphone sensors to map local variations. Teachers introduce students to magnetic mapping through simple compasses and GPS apps. In some regions, tourism projects offer aurora forecasts tied to geomagnetic activity, linking education with wonder. The field, once confined to technical reports, is slowly entering culture again, not as superstition, but as awareness. Looking farther ahead, space exploration will extend this awareness beyond Earth. Missions to the Moon and Mars are already equipped with magnetometers. They will record not just their own environments, but how the solar wind interacts with Earth's magnetic tail, which stretches millions of kilometers into space. When astronauts travel to Mars, understanding that magnetic connection will be vital for radiation protection. In that way, studying Earth's field becomes training for life beyond it. All of this points to a future where magnetism is seen not as background, but as part of daily life. Much as weather once became a shared language of experience, so too might magnetic conditions. A pilot checking solar activity, a farmer planning satellite irrigation, a teacher explaining auroras, each will be responding to the same invisible current. Awareness will not change the field, but it will change us. There is also something poetic in imagining the generations that will inherit this knowledge. A child born today will grow up in a world where the magnetic field is mapped in real time. They will watch animations of its flow the way we watch the tides. To them, the slow drift of the poles will be a familiar fact, not a mystery. They will understand that the Earth's heart moves, and that movement is beautiful. Perhaps that understanding will lead to a deeper respect for the planet as a system. One where core, crust, ocean, and sky are all parts of a single living mechanism. The magnetic field is not separate from climate or geology, it is their silent partner. Recognizing that unity may be one of the quiet revolutions of this century. And while technology continues to refine the science, the emotional truth remains simple. The field is both shield and signal. It protects us, and it reminds us of our connection to the forces that shape the universe. Each time a satellite sends back magnetic data, each time a camera captures an aurora, we're seeing ourselves reflected in the physics of creation. From a practical view, the field will keep acting strange. Its patterns will surprise us. The poles will continue to wander, anomalies will split and merge. But none of this is disorder. It is life in motion, the slow breathing of the planet beneath our feet. And in the end, that motion may be what keeps the world steady. At night, when the wind dies and the air grows clear, the magnetic field reveals itself. You cannot see it directly, yet its presence is everywhere. In the gentle pull on a compass, in the northern glow of auroras, in the hum of satellites moving across the dark. It is the unseen fabric that joins Earth to the sun, binding the ground beneath your feet to the sky above. Somewhere, deep below, rivers of molten iron flow around the solid inner core. They move slowly, carrying the planet's heat outward, spinning with the rhythm of Earth's rotation. Those flows are ancient, older than the continents, older than life. Their motion builds the magnetic field, pushing invisible lines through rock, ocean and cloud until they meet the solar wind. At that boundary, the field bends, forming the magnetosphere, our planet's protective skin. That skin flexes and breathes, it stretches when solar storms strike, then settles again. Sometimes it ripples for days. Satellites feel those movements as small surges of force. Sensors on the ground record them as faint tremors in direction and strength. Most of us never notice, yet every moment of every day, that shifting magnetism guards the thin layer of air that allows us to exist. If you could see the field as light, the planet would appear surrounded by a web of faint blue threads. They would loop from one pole to the other, curving outward, shimmering where they meet charged particles from the sun. At the poles, those threads would open like curtains, allowing some particles to enter, the source of the auroras that turn night into colour. To watch an aurora is to watch the field at work, translating energy into beauty. In a sense, each aurora is a message from the deep earth. The same heat that drives the core also drives the display above. They are opposite ends of one process: motion in the dark, light in the sky. Between them lies everything we call home. For most of history, people didn't know that connection existed. They saw auroras as spirits or omens, signs of weather or war. Only in the last few centuries did we begin to understand the truth, that those lights trace the invisible shield that keeps our world intact. The knowledge changes how we see them. What once inspired fear now inspires calm. The lights are not warnings, they are proof of balance. That balance is delicate. The field weakens, strengthens, and shifts as the core turns. It might someday reverse again, as it has many times before, but each time it does, life continues. The sky brightens with new auroras, the compass reorients, the field rebuilds itself. Change, even in the heart of the planet, is part of the same continuity that defines all living systems. Perhaps that is why the magnetic field feels more like a presence than a phenomenon. It doesn't demand attention, yet it underlies everything we know. It holds back radiation that would strip the air, it guides migratory species across oceans, and it gives our instruments a sense of direction. Without it, the planet would lose not only its shield but its orientation, the quiet order that makes navigation, weather, and even memory possible. Magnetism gives the world a sense of place. For scientists, that order is measured in numbers and maps. For everyone else, it is experienced through moments of awareness. A compass needle steady in the hand, a green light rippling over snow, a faint static hum on a radio during a solar storm. Those small details are the surface of something immense. The same field that touches your hand also extends 50,000 kilometers into space, where it meets the edge of the solar wind. The same energy that paints the poles also stirs the core of the Earth. This connection between the smallest gesture and the largest system is what makes the magnetic field so human to study. It invites humility. We can observe, simulate and map, but we're still part of the phenomenon we measure. Every heartbeat, every thought occurs within this field. Our brains operate through electrical signals, which interact faintly with the magnetism around us. Life and field are intertwined. The next generations of observers will see the field in ways we can only imagine. Real-time magnetic visualizations may appear in classrooms, planetariums, and even personal devices. Children might learn to read magnetic storms the way we read weather forecasts. Astronomers might map the field of Mars or study how interstellar magnetic threads link the galaxy together. The same curiosity that once followed the compass needle north will extend beyond the solar system, but despite the technology, the feeling will remain the same: quiet wonder at something vast and unseen. That feeling is what keeps people awake under dark skies, waiting for the aurora to appear. It is what drives satellites to orbit and scientists to trace faint anomalies in data. It is what turns an invisible field into a story worth telling. There is a calmness in knowing that this invisible shield is always there, even when it acts strange. Its movements may seem unpredictable, but they are part of a pattern much older than any human civilization. We live during a brief interval in that pattern, one moment in a long sequence of reversals and recoveries. The planet has endured every shift, and it will endure the next. If you step outside on a clear night and hold still, you may sense that continuity. The stars above move slowly, the air is silent, and yet the magnetic field hums through everything, through the soil, through the trees, through you. It connects you to the same processes that light the aurora and steer the compass. It has been here since the first spark of life, and it will remain after the last trace of human time has faded. The field may act strange, but it has always done so. Its strangeness is its nature, motion that never ceases, balance that never breaks. It doesn't ask to be fixed or feared, only to be understood. And so the story ends where it began, with a planet alive beneath its shield, and a quiet awareness that even the invisible can be beautiful. The Earth spins, the core turns, the field flows. Above the sleeping world, the magnetosphere glows faintly against the star, unseen, steady, eternal.